Okay, hello everyone. Well, first of all, I'm Antonio and she's Olena. We are from Matter Labs and Async, and we'll be telling you about the work we do to make sure that our prover, called Boojum, is safe. First of all, Olena will start talking about circuit bugs that are common, and then we'll tell you a bit about the tool that we built to deal with them. You want to take that?
Okay. So let's start from a question. Did anyone ever deal with circuits? Do you know how circuits look like? Okay,
Nice.
Great. We have one person. It's a progress. Second, did you ever deal with ZK bugs?
Nice.
Yeah. So it's ZK developer, right? Auditor. T developer. So because of most of you don't know what's ZK bug, we will start from small tutorial. So we'll start from type of bugs what exist. So, sorry. First, it's under constraint. Under constraint is the most common bug what exists in our industry. I mean, in circuits. It's usually if you have, this can lead to a Soundness bug when valid proof pass verification. So any witness what should fail with such under constraint bugs, it's you can basically prove wrong statement, right? So another bugs. Let's say I will show it like this. I will start from over constraint bugs. It's like when you can prove valid witness. So we have such constraint what can let you pass witness what's supposed to be correct. And usually we call it non-complete issue. But I will explain what's mean soundness completeness later. And here is a logical bug. It says actually there is no term in ZK industry, but we want to just mention that logical bugs is some bugs what we can catch with any tools, like static analyzer. So logical bugs could just catch with initial audit or Arena, code Arena, for example. Like person should look at this. So there is no AI or any tool. And it's also another type of bug, like type of bugs, duplication. Duplication is kind of bug, but it's still like, it's like overcomplicated the system. Arithmetic mistake, like wrong parameters. It's depend from developer. If developer choose wrong parameter, and it will won't be enough secure, and etc.
Yeah.
Okay.
Can I add something
Yes.
here? Throughout the talk, we will make a lot of emphasis on under constraint bugs. And the main difference between this and over constraint or logical bugs is that they are very hard to test for. So you can think of over constraint, where you cannot produce a proof for some input, as something that you can test by just generating a bunch of inputs, and hopefully you will find some inputs that you cannot produce a proof for. Same for logical bugs. Like if you implemented the EVM slightly wrong, you have a bunch of tests, and eventually you will find it. Under constraint can only be exposed by a malicious prover. And normally, it's very hard to test for that because the search space is absolutely huge. So yeah, that's why we will focus on these, because they are the hardest bugs to find. And also the most common, and also the easiest ones to make the mistake.
So another example, logical bugs, to make it clear, is like, let's imagine you're implementing EC pairing. And we tested like 2 points, G1 and G2. And basically, you need to do subgroup check for G2 point, because otherwise you can have subgroup attacks. So it's not something what we can catch with tools. Developer basically need to understand how to implement DC pairing, because otherwise it could be deal for some different attacks. So let's start explaining what's soundness. And you can see in a zero-knowledge system is sound if malicious prover cannot generate a valid proof or a false statement. It's clear, yeah. Usually we call such unsound bugs, we usually call under constraint. And why it's matter that without soundness, anyone could generate fake proof or break the system security. Second is completeness. Zero-knowledge system is complete if honest prover can generate a valid proof, or can't generate valid proof. Is a mistake. Can generate a valid proof for any true system. As I mentioned earlier, you have valid witness which should satisfy, I don't know, if a constraint Fibonacci generate proof for Fibonacci number, and there is actual some n Fibonacci number, and if we have some over constraint, it won't pass. So it's kind of problem, right? And why it's matter? We can just generate a proof for valid statement. So why it's important? Why it's important to have circuits without bug? Because our mission is to become decentralized. And if to compare with solidity bugs is actually kind of easy to see some anomaly. Yeah, it's either someone steal money or no. But with circuit bugs, someone malicious could find such backdoors, can find a bug, and can generate a proof, and we wouldn't like even know. And it will every time fake proof, and it's like kind of dangerous, and it's without clean circuits, we wouldn't be decentralized.
Can I add something? Yeah, and to again go back to the over constraint and under constraint, completeness and soundness. Right now, a completeness bug would be worse for us and for any CK rollup, because it would mean that we cannot produce a proof for a valid transaction. But that's a liveness issue, which is bad, but not the worst. A soundness bug would mean that someone can produce a proof for an invalid state transition, which might be awful. The thing that saves every CK rollup for now is centralization, because that would require a malicious prover, and right now, no CK rollup is open to submitting a proof permissionlessly. But that's not going to stay forever, and very soon we should move to a situation where anyone can submit a proof for a new state. And so we need to make sure we don't have any soundness issues.
So anyone who familiar with bug bounty program, you can see that for solidity bugs, actually people pay more, because you can exploit right now solidity contracts, right? Exploit bugs in contracts, but because we centralize, no one except us generate the proof. So as I have to say, you basically don't need our prover, you just need a malicious prover to exploit bug, and yeah. From our side, it's just circuits and verifier, what we probably will produce. So let's start from examples. So like small tutorial. The most popular is Boolean under constraint, and in this example, you say a long integer addition. So we have in input A, B, what's check, range check, and everything. What we just add this A, B, yeah, long chunks addition. And you can see there is a constraint chunk size when we add this. And also you can see decomposition. Why we need the decomposition? Because we need this bit value for checking for overflow. And then you can see that we allocate result and bit, and do actually in the end and for 32 bits a range check. So do anyone notice here some mistake?
I do.
That's great. But do you need time, or should I already reveal?
I think you can.
Reveal. Okay. Problem is that we allocate number, but this is actually bit. It's either 0 or 1. For Boolean, we have special constraint. So what we make sure is that with this constraint, we make sure it's either 0 or 1. So if you, all constraints is kind of a polynomial, right? So this is polynomial what's actually represented Boolean. And only two roots allowed. So this equation have only two roots and 0 or 1. So you can put any numbers there. It's how kind of constraint works. So, and normal allocating, we just add number in execution trace and doesn't constrain anything. But for Boolean, it should be separate constraint. So another example, range check under constraint. So the same example, previous one was pseudocode written by me. Maybe it's not accurate fully, but this one actually from our Boojum code base. And you can see the same, like a long subtraction. We already have checked A, B, and we kind of do the same. We have borrowed bits, result, initialize result, variable, empty variables without any witness. And then we do addition inside. So inside perform subtraction is already like constraint what prove valid subtraction. But then we do borrow. We allocate borrow, so we get this new borrow, and we kind of inside from variable checked do this Boolean constraint. And here is also a mistake. So second try. If anyone wanna. So okay, it's a hint. Did you notice I mentioned a couple constraints in previous examples? In the end, we do something. No, I wanted you to try. Which constraint we missed? Which constraint exists in this example but doesn't exist in next?
The 32-bit range check.
Yes, exactly. So when we do any manipulation with a number, if we like chunk a bit, or if we do addition or do multiplication or do subtraction, we get result. If we expect that the result should be U16, that we need to check that it's no more than 16 bits. Because currently variable, it's live over our field. In Boojum, field is Goldilocks. So it currently could be 64 bits. We could put 64, like if a malicious, it could be 64 value, but it will still satisfy constraint, and it will be like wrong result, actually. So, yeah, I show here, like how it should look like. 16, yeah. And let's look, you can read it the same what I said, but let's look how we can do range check. So there's two popular way in our system. It's a bit decomposition. It's when we basically prove this linear combination where base 0, b1, b2 is a bit, 0 or 1. And when we do this decomposition, we like take a number, a cut by bits. For each of bits, we need to do a Boolean constraint. And it's kind of expensive. We need like for 16 bits, 16 Boolean checks, and then do linear combination. It's like a lot of constraint, right? If it's what if it's like we need to check 256? It's minimum 256 range check bits, and I mean decomposition entire constraints. So, and there is alternative, is kind of lookup array check. It's when we pre-compute lookup table with all combination from 0 to 16 bits. And we take a result and just check is it result exists in this table. If it exists, that it means it's lay in the size limitation, or if it's not exist, this will be basically error. It won't satisfy. Problem with this method is that we have kind of limitation in prover. We can generate a lot of lookups. We can generate 8, 16, 64. Because it's like we will overhead prover, right? So depend from But basically, we were working on 16 and 8 bits. It's kind of enough. So another popular one, mistake, my favorite actually, because I found in a email this bug. This is mul and div under constraint. How usually ZK developers represent mul and div. So this is this equation, and quotient multiply p is our module plus r. It's our reminder, but it's also we return reminder as a result. It's because we work in modular and arithmetic. So first of all, we need to check if it's A and B is normalized. Normalized it means laying in our model. If we not normalize, it doesn't. If they not normalized, we need to do some reduction. Yeah. Second is it's important to, because Q and reminder, we actually it's like witness. We get witness from nowhere, from our prover or our witness generation or malicious witness generation. We need to make sure that this is lie in the range check. Depends what size you in the, like. If A be 16, then QR should be not 16, 32. R should be 32 because of 2n. So you need to range check these two witnesses. It's a kind of also mistake, and also you need prove these linear combinations that left part equal right part, and there is actual common bug what I wanna talk about, that we don't prove that reminder actually smaller than our model. So because we don't do this, we can find two variants of witnesses what can satisfy those constraints. And we can take reminder of a bigger than model, and it will satisfy all constraints, all range check, but unfortunately it will be the different results. So it's a kind of a small tutorial about these basic bugs. The most popular I would say it's range check, so really easy to forget. And now we start from our Beaver. It's a static analyzer. And what actually Beaver check, it's a check that we have soundness, completeness. Also, he kind of could improve efficiency, because it's we check for duplication. Yeah, we can simplify our system. And actually, it was inspired. Maybe you'll say this.
So yeah, the work was inspired by a similar static analyzer called Picus, built by verifies. Their system was targeting CIRCOM, and because CIRCOM is in R1CS, that means that the constraints are very uniform, and therefore it's reasonable to expect that with a few rules plus an SMT solver, you can find bugs. The thing is that in Plonkish, if you're familiar with, we have very heterogeneous constraints. So SMT solvers and these small rules are not going to make it, are not going to cut it. And further, we are targeting much bigger circuits. The work that they did for CIRCOM was targeting in the hundreds of constraints, while we have millions and tens of millions.
So the thing is that our circuit analyzer just worked for our system. But we presenting idea because we think this idea could be implemented on any another rollup, ZK code. And the thing is why it worked for us, because we have all these constraints. What do you see? It's actually hard-coded gates in our system. So it was easy to make each rule for these gates. We will talk what rule I mean, but let I come back this one.
Yeah, thanks. So we've seen a bunch of examples of bugs. Finding bugs is great, and we do audits, and we audited the code ourselves. But what's cooler than finding bugs is to prove the absence of bugs. I think everyone can agree on that. So before we start talking about how we do it, I wanted to stress in this slide a bit the point of why we think under-constrained bugs are so common. And I think this is because people, when we write code, programmers, we think of code as a function, essentially. We have some inputs, and we produce an output. And this means that we have determinism over the inputs. But when we write a secret circuit, what we are actually doing is encoding a relation. And not all relations are functions. And we'll see how this comes into place. For example, let's say we are trying to build a function is0, where we take a variable a, and we return either 0 or 1, depending if a is 0. We can see how we encode the circuit on the left with just two simple constraints. We don't need to work through them right now, but you can look at it later and see that for any value of a, if it's 0, b must be 1, and otherwise b must be 0. On the right here on this slide, we have the functional view. So we have that if the a is an input and we have the value, then we can assign values to both b and the intermediary variable b1. The problem is that this is called the witness generator normally, and we cannot trust it. This is part of the prover. The only thing that the L1 will verify is a circuit, which is on the left, or the constraint system. So for instance, so you can work through the example, but if we had forgotten to add the second constraint, then we can think of what would happen with a value of a equals 0. So if a equals 0, then the left-hand side of the constraint is 0, and 1 minus b must equal to 0, so b must be 1. We are good. But for any other value, for example for 1, we will have that v1 is equal to 1 minus b. So essentially, we can put as an output any other value. And right now, what would happen in the rollup is that we will keep running the code on the right, which is the witness generator and the prover, and we wouldn't notice because the 0, the valid value, is still allowed. It's still accepted. But as soon as someone malicious can tweak the code on the right, they can break everything.
Okay, think about like we work in a prime field, and it's a finite field. It's a finite amount of numbers, possible values, right? And what we actually do is constraint. We kind of make it subfield, also finite field, but already with some limited amount, like constrained amount of possible values, what could satisfy our circuits. It's like on an example of Fibonacci numbers, we will have Goldilocks field. It's a I don't remember how much elements. It's like 264 minus
Goldilocks?
Yeah.
Yeah, it's 264
elements. Yeah, but Fibonacci is also like it's a smaller subfield. So from all this in our field elements, there will be Fibonacci numbers, and constraints kind of work that we like cut pieces, right?
Okay, so here we are going to talk about Beaver, which is the tool that not only finds bugs but also tells us if a circuit is actually sound, sometimes, a lot of the times. And how does it work? Okay, so it works in different stages. The first one is to capture the circuit, and this is what we were talking about with custom gates. So a lot of the custom gates have a lot of semantics. So for example, if we had an addition gate, we know that if we have a plus b equals c, that if we know the values for a and b to be, let's say, determined, then we can know that C will be determined. But not all gates are like this, because some gates are just asserting something and they don't follow an input-output relation. Then we do a quick check that is just to check inefficiencies, which is called duplicated detection. I'll talk about it in a second. And then we start doing the interesting passes. First is the range propagation, which is just collecting information about which numerical ranges each variable should be in, and propagating this information through rules. After that, we can do a pass that we call type checking gates, which is quite simple. It's just saying if this gate expects to have a variable of U16, that variable should be checked to be in the U16 range. Then the final pass is called uniqueness propagation, and it's basically where we get the soundness. I'll explain that later. And yeah, with this information, we can perform the soundness check. So as I said, we are working in Plonkish. We have a bunch of custom gates. Some of them have this functional relation, but not all of them. So what we do is that for each gate, we collect extra information. So for example, the input and output variables, if they are an input-output relation, or if it's an assertion, the output variables will be just empty. And the most important part, other than that, is that we each gate can declare if it's checking some ranges of some variables, for example, lookups, as Olena explained before, or if they require some range checks. So for example, if we have a gate for U16 addition, maybe we don't want to enforce the range check every time because we might incur in duplicated checks. So we will have individually unsound gate that we then make sound by checking once with a separate gate. So this range checks required is the thing that allows us to type check gates, as we'll see in a second. So first, duplicated gates. This is very trivial, but it's fun. Essentially, a duplicated gate is a bit more interesting than it might sound, because, for example, let's say that we have a gate that has an addition relation. So we have A and B as inputs and C as output. And we have two instances of this gate. We have these two where they share the same inputs, A and B, but they have different output, V2 and V3. Here, even though it's not exactly the same gate, we can get rid of the second one and replace every occurrence of V3 by V2, because they must be the same value. So, yeah.
I want to add that in our system, we have a bunch of #stat and #3 where we kind of store our gates. And basically, it's another way how to prevent duplication. Just reuse constraint what's already in your kind of tree. But not every time it's working right.
So we try to avoid this duplication, but we sometimes miss it. So then we start with the interesting stuff, range propagation. So how do we get range information? Through range checks. So there will be gates that will say, okay, this variable is in U8, and we know that it will fit in 8 bits. But then we have operations that are closed under a specific size. So for example, the first rule you have there is A times B, which could be seen as a Boolean conjunction, A and B. And we know that if we know that A and B are Boolean, then the output will be Boolean, because a conjunction is closed under Boolean. And with a bunch of rules like this, I didn't add all of them, so we have arithmetic and also control flow, we can propagate this range information forward from the range checks to the rest of the circuit. We also do some constant folding and some custom rules, but I don't think we have time to get into those. With the range information that we collected, we proceed to do the type checking pass. Essentially, just go through the circuit again and say, okay, this gate requires this variable to be in this range. Let's check if the circuit had enforced this. This might seem a very dumb check, but with this we found at least 2 critical bugs. And then we get into uniqueness propagation. We say that a variable is unique if there is only one value of the witness for it that can satisfy the circuit. And basically the idea is that we will start with assuming that the inputs are unique, because they are given by the verifier, the public inputs. And we want to see if, given those unique inputs, we can show that the outputs of the circuit are unique, meaning that the circuit is deterministic, is a function, is sound. So we will exploit both the input-output relation of some gates and the rules that we will show in a second. So yeah, this is what I said. And after propagating this uniqueness property, we will just check if all of the outputs of the circuit are unique, meaning only one value of the witness can satisfy the circuit. So let's start. So I'm not going to get deep into how to read these rules, but let's look at the first one for a minute. So here you see that what we are building is, so we have a constraint that is representing a linear combination where the coefficients are of the shape 2 to the power of k times I. Well, not k times I, k sub I. And we have variables. And essentially, this is just similar to the bit recomposition that Olena was talking about, but this could be any kind of lim decomposition. So just breaking a big number into smaller chunks. You can think of it as U8 chunks. And so we know that if the single variables satisfy a given range, and the output of the linear combination is unique, then we know that each individual chunk is unique. Because for any given number, if we have a well-constructed base, the decomposition is unique. The simplest case is if we want to split a number into bits, we know that there will be only one binary decomposition for that number. So let's go into the results, and then if we have time, we can do a little demo. So first of all, the most important thing we wanted to check is sound circuits. We've shown that all of our hash functions circuits are sound. Well, they weren't, but we fixed them, and then we proved that they were sound. We also proved that the recursive verifier is soundish. I'll get to that in a second. And for the big CKVM circuits, we proved 8 to be sound. Some of them were very tricky and would take a lot of work to do. But in theory, we could continue to prove it. We have to do that. We have to do that. So we have like 15, so a little bit over half. Regarding bugs, we found 3 critical bugs in Boojum, and one unsoundness that is non-exploitable. So that's why the recursive verifier has an asterisk. It's not technically sound, but for all intents and purposes, it is. And inefficiencies. So remember the duplicated gate check. So for most circuits, it's negligible, the duplication. But in some, we found up to 9% of duplication, which, again, it's not deal breaker, but it's nice to find and to fix. So that's it for the main talk. If we have a minute, we can go to the demo. I don't know how we're doing on time.
Let's question and then think maybe demo.
Yeah.
So also I want to add that even though that we found a bunch of bugs, it's still try to encourage people to search for bug. We have like a bug bounty program. We have different hackathons, you know. So would I say circuit is sound? Yeah, but there is possibilities. There is some sneaky bug, and you can try to get lucky to find it, and then you get some bonuses.
So yeah, I guess we can move to questions, and then we can do a little demo if anyone is interested. Yeah?
How long does it take to run the static analyzer for?
Depends on the circuit size, of course. As we can see, for a smaller gadget, which is just like a component, it takes a few seconds.
Yeah.
For the bigger, like several million constraints, it can take a couple of minutes, okay, but not too bad.
Yeah, still manageable.
Yeah. Yeah, but that's the point. That's why we are not using SMT solvers. If we were using SMT solvers, we would be doomed.
And what would that provide? Like
automation. So we wouldn't need to do as much manual work into figuring out the rules that I was showing.
I see.
It's a trade-off.
Yeah.
Yeah?
Is the uniqueness check probabilistic?
No.
How does it work?
So
Can you give an example?
I can give an example. Well, okay, but maybe before the example, just to explain it a bit better. Let's say.
Look up.
No. Let's say the binary decomposition. Let's say you have a number that is supposed to be a byte, 8 bits, and you have a circuit that checks that the 8 bits recompose to that. Yeah. Normally, instead of doing the divisions and stuff, what we do in a circuit is do the inverse. The witness will provide us an oracle. They will provide the 8 bits, and we compute the recomposition and check that it's equal to the original number. Yeah? So what we do is that if you know that the original number is unique, because it's an input, we can safely say that the bits are unique if the bits are asserted to be bits, so they are Boolean checked, and they recompose to the original number. Because we know that any number in the range of U8 will have a unique 8-bit decomposition. Does that make sense? So with these sort of rules, there are rules for other operations, you can propagate from inputs the uniqueness forward.
The thing is, we already know what should be unique and what shouldn't.
Let me give a quick demo. It's gonna take only 3 minutes. Can you see the screen?
Yep. Yeah.
So this is actually code that we have in Boojum. So there I run the analyzer, and you can see some output on the right, saying, for example, that that we have some duplication, like 0.25% negligible. But then we see that not all outputs are unique. And we, in order to help us debug, we say which output variable is not unique, but also which is the first variable on the witness, on the trace that is not unique. Here we see that it's variable 253, which is involved in this gate only, which is a reduction gate, linear combination gate. And if you look at the coefficients of this gate, you can easily see that it's computing a chunk recomposition. So if you investigate a little further, you see that this output goes to variable 262. So you start saying, okay, give me the gates where 262 is involved. And same thing, it goes in the one that we created, and in the next one, it's part of another linear combination going into 263. We do one more, and we see that again it fits into another linear combination with increasing coefficients that end up in 191, sorry. This means that we are chaining 3 gates to recompose the value of 191 into smaller chunks that we range check. We can say, okay, now 191, is it unique? Yeah, it's a variable index or variable name. And now we know that 191 is unique. This is what I was saying, like the number that we are decomposing into bits or into chunks. Then we can ask it, is it bounded? Yes, it's bounded, and it's by 25, which is much smaller than what we actually expect. So we go back to looking at the constraints, and we say, okay, tell me about the little chunks that we should be asserting to be into the size of the chunk, either bits, or in this case, I think 8 bits. And we say, okay, give me the range for 253. And there's nothing, so we are not range checking it. So if we look, and I will shorten some debugging time, we see that this is coming from SHA-256, from function, expansion, split and rotate. And you can see the code here. So I'm not going to go deep into it, but split and rotate is just splitting bits and rotating them.
We basically perform, like,
Yeah,
we
well,
have a value in cuts, we do something with size.
Yes. So we are generating new bit chunks, like I think 8 bits. But the generated ones need to be range checked because they need to be into these 4-bit chunks. And we do it by using a lookup table in the XOR operation here. The problem is that this goes into that goes into that, but for this one, we first overwrite some of the variables here. So those variables will not go into the lookup table, so they will be never range checked. And therefore, we cannot have soundness, and a malicious prover can use variable values that are over the U4 range to manipulate the SHA hash. So the simple fix is to come here, and before overwriting them, just adding, here I'm doing XOR just because it uses a lookup table and range checks, but we ignore the result. And now that we added the range check that we were missing, we can run it again. It's gonna build for 1 second. It takes longer to compile than to run. Maybe, but okay. Now we get that it's a sound circuit after the fix.
Yeah. there is a interesting trick why we actually use XOR table. Like why it's not the range check table. The thing is, to not to spam a lot of table. So actually XOR table have 3 keys and 1 output. So we basically do XOR between these 3 values, like 8 bits, 8 bits, 8 bits value. But the thing is, key themselves is already range check. And if this key already exists, that means it's like in this range, right? So to save place on the lookups, we will like reuse XOR, but you can see, but then use XOR. We just check.
We ignore the output variable, basically. Because
strict XOR menu, it will return for your XORed value, but we don't need it. We just check if these keys exist. And also you can see, it's a, I could say what kind of trick we use. It's a range size propagation.
Yes.
Yeah, but actually uniqueness propagation will basically will work the same. They both like kind of
no, this
good.
Is both. This is range. So for the uniqueness rule,
you
need range information for the hypothesis.
So they basically have the same like logic and work the same. Like.
Okay, that's it.
Okay. Any question? Last time.
Then we're good. Thanks a lot.